pulse sampling and reconstruction. So our aim is to understand the fundamental process in converting analog signal into discrete one. To convert analog signal into discrete signal, the primary function is sampling. Sampling is a process of converting continuous time signal into discrete time signal. So the statement of sampling theorem is as follows. A band-limited continuous time signal can be sampled and perfectly reconstructed from its samples if it is sampled over twice as fast as the highest component of that signal. Here, the sampling signal is a periodic train of pulses having unit amplitude and sampled at regular interval of time Ts, which is called sampling time. In this experiment, we validate the signal reconstruction for the following cases. Here Fm represent message signal frequency, that is the highest component frequency component of the message signal, and Fs represent the sampling frequency. So we'll verify for undersampling, ideal sampling and oversampling which sampling yields the better signal reconstruction. So this is the general circuit for understanding the sampling process. Here the transistor is operated as switch. This function generator acts as message signal and this function generator acts as the sampling frequency. So here the transistor is operated as switch here. Whenever base voltage is available here, transistor is driven into saturation, therefore the output will be 0. Whenever the base voltage is not available, transistor is in cutoff, that means open condition or open circuit, therefore the message signal is available across the load resistor. Hence, we can able to observe a sample taken for particular instance of time. So this simulated waveform shows the sampling pulses and the sinusoidal wave and the output. Here we observe that VB is 0 here. When VB is 0, transistor is in off condition. Therefore, this instance of the amplitude of the message signal is available and it is appearing across the load. Here VB is high, that means this voltage is sufficient to turn on the transistor. Therefore, transistor will be in on condition. Therefore, it acts as a short circuit. Therefore, nothing is available across the load here. Like this, the samples are taken at regular interval of time. So now we are going to verify the 3 conditions which we stated earlier. Here we have considered message signal frequency 100 Hz and the sampling frequency 50 Hz, much lesser than the message signal. On simulating, we are going to analyze the output here. The sampling frequency is 50 Hertz, if we consider in time, 50 Hertz means 1 by Fc, that is 20 millisecond. So for 10 millisecond transistor is on, for 10 millisecond transistor is off. So here we are going to consider the periodic pulses are having 50% duty cycle. That means off time is equal to on time. So during off time, when VB is 0, the sample is taken from the message signal and it is available here. Whenever base voltage is available for 10 millisecond, the transistor will be in on condition. Therefore, the output voltage here available is 0. So here the output wave is not exactly matching with the message signal. So from this analysis, it is clear that lower the samples, signal cannot be constructed. Here we are going to increase the sampling frequency from 50 to 200. That is, Fs is 2 times Fm, exactly twice the highest frequency of message signal we have considered. If Fs is equal to 200 Hertz, time is 5 millisecond here. Therefore, we are going to see here 2.5 millisecond this is on, and for remaining 2.5 millisecond it is off. So we are able to see the sampled output because of the transistor acting as switch. Whenever VB is 0, for 2.5 millisecond sample is taken, and for 2.5 millisecond transistor is on and no sample is available here. That means enough samples are available in order to reconstruct the signal. So now we are going to consider the sampling frequency much higher than the message signal. So we are going to consider here sampling frequency of 1 kilohertz, which is 10 times higher than the message signal. So the sampling period will be 1 millisecond here. 1 millisecond means it is divided equally 0.5 millisecond on and 0.5 millisecond off. So for 0.5 millisecond, here VB is available. Therefore, transistor will be in on condition and no sample is taken. Here, for 0.5 millisecond, VB is 0. Therefore, transistor will be in cutoff and the sample is available for 0.5 millisecond. Like this, many samples we can observe on this waveform. This tells that higher the sampling frequency, more samples are available to reconstruct the signal. So this is the reconstruction circuit where a capacitor and resistor are connected here at the output of this transistor. Here we are able to see the reconstructed wave frequency is matching with the message signal that was sampled earlier. The conclusion of this experiment is sampling is the primary function required to convert analog signal to digital signal. The remaining two functions are quantizing and encoding. So we have analyzed three different cases: undersampling, ideal sampling or Nyquist rate sampling, and oversampling. Undersampling, samples are available is very less, so it is very difficult to reconstruct the signal. Nyquist rate, samples are available, we can reconstruct the signal. But in oversampling, more number of samples are available, hence we can reconstruct the signal clearly. So this block diagram shows the process of converting analog signal into digital signal. In digital signal, the signal is represented in terms of binary 1 and 0 as shown, whereas here analog signal, amplitude of signal is defined for all the values of t here. So the first process is sampling, which converts analog signal into discrete. This experiment we have completed here. So the next two important functions are quantizing. It is nothing but representing the discrete level taken from the signal to the nearest digital level. That is quantizing. The next process is encoding, where we are assigning the binary code for each level in order to get the information ones and zeros. That is how analog signal is converted into digital signal. In the coming lab session, we are going to focus on quantizing and encoding. Thank you. Keep learning.